at the University of Maryland, College Park. He received his PhD from Harvard University in 1988, which for those of you who are in my class know that's right around the time when Antarctic ozone hole was becoming a big topic, and his dissertation was on the Antarctic ozone hole. And following his postdoc at Harvard, he spent 13 years at the Jet Propulsion Laboratory in Pasadena, and then joined the faculty at UNCP as a professor in 2007. He publishes on a wide range of topics from stratospheric ozone layer, air quality, carbon cycle, and climate, and is the lead author of the 20 questions and answers of the ozone layer, published by the UNEP. He is also a fellow of the AGU, American Geophysical Union, and American Association for the Advancement of Science. So I'm very excited to have you here. Thank you so much for making the trip over.
You're welcome. My pleasure. Okay, so thanks for that great introduction. I actually hear that there are folks in the room who use the 20 questions and answers in their class. So now you'll be able to hear from me what's up in that. I'm going to use it heavily. So this is a figure showing how the thickness of the ozone layer has evolved over time. I'll explain why it went low here. Some of you know, and look, it's kind of leveling off here. It shouldn't be doing that. It should be going up, but it's not doing that. Here are some of my sources for information. There's not a mouse. Okay, I'll just do the clicky thing and let's see. And you can see this, but it's hard to see. Okay. And sorry, getting used to this. Okay, my sources, the 20 questions and answers, a paper that Megan is leading that's under review right now, and then a few papers that someone named Laura McBride and I are leading as well. Here's what the ozone layer looks like in other regions of the world. So I'm going to tell a story in two parts, the past and the future. And I'm going to tell quite a story. The guiding principle for the story is going to be the timeline for the 20 questions and answers, which is coming up in a minute. So here is what the thickness of, or the concentration of ozone looks like. We called it abundance here to use a more common word, as a function of altitude. And what we're worried about is the area to the left of this curve. We integrate the concentration of ozone with respect to height to get the column abundance of ozone. And so in this figure, these are satellite measurements of the concentration of ozone, largely a little bit of ground-based stuff further back that allow us to see how the thickness of the ozone layer has evolved over time. And we care about that because we have observations that show that as we deplete or change ozone here, the changes are huge because we're going to different geographic regions. We're going to South Pole where we have the ozone hole that I'll talk about soon. What we see is that for about a 50% decline in ozone, we have about 100% increase in UV light. So for 50% decline, 100% increase, I want to put my cursor around here so it doubles. Now, we also know that for every there's about a 1-to-1 relationship between the rates of melanoma skin cancer and UV and a doubling for non-melanoma. So in other words, for every 1% drop in ozone, we have a 2% increase in skin cancer incident of the scary kind that you never want to hear from a doctor, and the less scary kind of 4%. And we know that from epidemiological data such as this. This chart here shows the rate of skin cancer incidence as a function of something called the Robertson-Berger UV index. It's exposure of a population, in this case, white males, and the folks who live in Albuquerque, New Mexico, are closer to the equator where the sun's higher in the sky and where ozone is a little bit less compared to people who live in Seattle, Washington, which is rainy. We see about a 2-to-1 relationship between UV exposure and this UV index. This is a log scale. On this side, I'm showing for females, the scary cancer melanoma with about the 1-to-1, And this was published way back when. And I actually grabbed this figure from my PhD dissertation, which I had put in there. So this is some epidemiological data. All right, now this will be a figure we're going to see a lot here today. It is a modified version of the introductory figure of the 20 questions and answers. To remind everyone, CFCs are molecules that contain chlorine, fluorine, and carbon. And the first thing that I would like to talk about is the CFC ozone depletion hypothesis that was put forward in 1974. And I want to pause, catch my breath, and say that I'm happy to take a moderate amount of questions during this talk. So if you have questions, raise your hand. I'm happy to answer any questions so far. Okay. So in 1974, prior chart, these two guys, Mario Molina and Sherry Rowland, published a paper linking CFCs, which were used as aerosol propellants, they were used as refrigerants, and they were used as solvents in the electronics industry. They linked that to ozone depletion. And their hypothesis was that these gases, which are represented here in yellow, would rise through the atmosphere because they were biologically and chemically inert down low. They would be transported to the stratosphere. They would be lost because of the intense UV radiation in the stratosphere, and their products would go to CLO, chlorine monoxide, which is a radical that destroys ozone, chlorine nitrate, HCl. The green, blue, and blue are what we call inorganic chlorine. They've lost their carbon. Here are the chlorine source gases are all organics. Now, their 74 paper, if you go back and look at it, was sort of like a sketch. It was before we had serious satellite observations, before we had serious computer models. There was a lot of, if we assume this and we assume that. And people knew about chlorine and ozone published before them, but they were worried about rockets putting chlorine in the stratosphere. So they didn't invent the chlorine and ozone. They connected the dots in a very elegant way. And it's amazing because a lot of the assumptions they made in their paper turned out to be true. So true, in fact, that this is how it ended for them. You ready? It ended very well for them. My timing is off. It ended with the Nobel Prize. So this is Sherry and Mario receiving the Nobel Prize from the King of Sweden in 1995. Ended very well for them. Okay, so by 1978, the US, Norway, Sweden, and Canada banned the use of CFCs as aerosol propellants. And I will say, looking around the room, I don't think there's anybody in the room who knows what the most popular TV show in the US was in 1974. Anybody know? Well, if I tell you the name of the lead character on the show, you will know immediately. Archie Bunker, All in the Family. And there was an episode in All in the Family where the great Rob Reiner, who played Mike, yelled at Gloria, his wife, that she should stop using hairspray because it was destroying the ozone. And Gloria goes, "What's the ozone?" I mean, my teenage years were very different than your teenage years. In my teenage years, everybody watched All in the Family, and that's all we talked about the next day. Seriously. So if you get this on a TV show like All in the Family, it has huge public resonance. And Rob Reiner was way ahead of his time. So anyway, we banned the use, but only one use as aerosol propellants. Ah, good, the button works. And so here's where we are. Now, this chart on the bottom shows the emissions of all the source gases that deplete ozone that we estimate occur to the atmosphere, and we weight them by something we call the ozone depletion potential. These are atmospheric emissions. They are different than industrial production. I will soon come to industrial production, but atmospheric emissions include production and leakage, as well as CFCs that may have been made years ago that get released to the atmosphere by decaying equipment, or they were used as insulation in buildings, and when the buildings are torn down, the CFCs get released. Okay, so this is 1978. So in 1985, something amazing happened, and that was the discovery of the ozone hole. So a man who was knighted for this work, Sir Joe Farman, published a paper in Nature, and they wintered over at Helley Bay, Antarctica, and they had this graph showing the total thickness of the ozone layer over the research station going down. And I mean, it's a pretty precipitous drop, and you would think maybe they would have raised the alarm here or here, but they wanted to be sure, and it was only during 1 month, and they were just collecting the data, and other people weren't seeing it. In the paper, they related this in a hand-waving way to the atmospheric rise of CFC 11 and CFC 12. Those are the circles. Now, it's a long story that I don't have time to get into, but when NASA looked at the data from the total ozone mapping spectrometer that was put up in space to actually measure this, they saw the same thing. But originally, there were doubts about the data. It's a long story. Anyway, they published this paper in 1986 showing the ozone hole, the development of the ozone hole over Antarctica, and this got a huge amount of attention. And here is a little sketchy animation I put together showing the abundance of total ozone in 2001 from a satellite instrument. And basically, there's a circulation of air over Antarctica called the polar vortex. It gets very cold. It's very isolated from the rest of the stratosphere. And we now know that ozone gets incredibly low. And we know it's due to CFCs. But how do we know that? Well, in 1986, there was an expedition to go to Antarctica. This is the McMurdo Research Station as it looked back then. This is a photograph that my colleague Jeff Toon took of the expedition. Notice the airplane has skis. Notice the engine propellers are still moving. Great exposure here. Notice the fellows are running. They're urgent. And this is Susan Solomon, by the way, who led the expedition. And this was a bittersweet day for Jeff and Susan because they were leaving the ice after a job well done. Job well done. So here is one of the most important observations to come from this. This is the average of ozone that NOAA was measuring over this time period from the South Pole. This is what they measured on October 7th on this day. So a reduction of 130 Dobson units, a huge bite out of the ozone. Remember, every 1% drop in ozone, we get 2% increase in UV. So we're getting a massive amount of UV light hitting the surface of Antarctica, and there's things that live on the surface of Antarctica. And we know from observations like this that chlorine is responsible. Let me explain this. This comes from two papers by Bob DeZafra and Phil Solomon, no relation to Susan Solomon. And this shows a profile of the abundance of CLO, chlorine monoxide, a radical that depletes ozone as a function of altitude. And Molina and Rowland predicted it should maximize at 40 kilometers and deplete ozone up high. There's not much ozone up high. If we depleted all the ozone up high, we'd have a slight increase in UV light. There's a huge amount of ozone down low. Huge amount of ozone down low, but down low, we don't expect there to be any CLO, yet there is. And this graph here shows the abundance of CLO as a function of time that they measured from the ground based on various assumptions. This is basically, various assumptions about what altitudes CLO is at. So this is remote sensing. Now, see, Molina and Rowland predicted this. Down low, we expect all the chlorine at 20 kilometers. 20 kilometers is important, 15, 20 kilometers, that's where we're losing the ozone. Down low, we expect all the ozone to be in the form of chlorine nitrate and HCl, which we call reservoirs, because they don't lead to ozone loss. So, long story short. It's the presence of the cold temperatures that lead to clouds. I took this photograph of polar stratospheric clouds in Kiruna, Sweden in January 2000. I almost got frostbite doing it because I used a film camera with slide film, even though, this is the infancy of digital cameras, and I had to keep running in and warming my hands and hoping the slide film didn't crack in in the camera. Okay, so the polar stratospheric clouds lead to surfaces, and the surfaces lead to heterogeneous reactions, surface-mediated reactions that convert all the reservoirs to CLO. Susan Solomon developed this theory. We added the bromine part. Brian Toon did the PSC falling part. We think nitric acid is kind of like the immune system of the stratosphere, but condenses into PSCs and falls down. Long story short. Okay, 1987 was an aircraft campaign to Punta Arenas, Chile, and Jim Anderson and his group at Harvard measured CLO from an aircraft, which with much better precision than the ground-based remote sensing. Here's ozone before we have sunlight. Here's, what is this? 3 weeks later, CLO is high. Here's the chart. Here's the axis for CLO. Notice the anti-correlations between ozone and CLO, a really strong anti-correlation. I defended my PhD thesis in January of 1988. And I said to my, what am I going to do if they don't find high CLO? My advisor assured me it would be okay, but we were nervous. We found out about this literally 20 minutes before the press conference. We had someone call us and read us the transcript. I think I know who, but I can't say. Call us and read us the transcript. And this was so we could relax in the room before the press conference. Quite a time to be a graduate student. Okay, I don't know why this slide is blank. That's why it's blank. So this is a very famous observation. This is a photograph of the stamp commemorating the observation. It's called the ozone hole stamp. I obtained this high-resolution photograph of a stamp of walking into a stamp shop in London, England, I don't know, 10 or 15, maybe 20 years ago. And I said to the guy who was dressed in a tweed jacket and very proper, hey, do you have that ozone hole stamp? And he said, oh, yes. And he just walked right over, grabbed the book, how many do you want? He didn't have to look it up. Okay. So here is from the 20 questions and answers. Look at the rapidity in which the ozone hole developed. And it developed with this great rapidity because we were still using CFCs like crazy. Back then, rising. By 1989, we established that the ozone hole is caused by CFCs and halons. They supply bromine. Halons are like CFCs, but also contain bromine. This was established at this time, and the Montreal Protocol was in place. Here's 1989. Oops, I don't know what happened to this. This graph, no, it is, okay, it's at 1989. So this is basically just after the peak of the atmospheric release of CFCs. So basically what was happening is that as the science was happening, the Montreal Protocol was being tightened. If there was no protocol, EESC, a quantity that Megan and I talk about a lot. It stands for equivalent. Do I have to talk about it? No, there's a spot on the screen. Equivalent effective stratospheric chlorine, EESC. It's a way to combine chlorine and bromine, put it into a single number. Without the protocol, we'd have kept rising. The initial Montreal Protocol was pretty tepid in slowing it down. It was brilliant by having a way to keep meeting, and as the science advanced, keep ratcheting it down. But it's easy to say we should ratchet it down, but the world's using these gases, and we have to replace the gases with something else. And as I'll get to in a moment, CFCs replaced with HCFCs not as damaging the ozone layer. The CFCs, eventually HCFCs were replaced with HFCs, which do no damage to the ozone layer, but do something else really bad, which I'll talk to. But anyway, this was all in. So a big time here between 90 and 92, we really figured out how to do this right. And there was court testimony at this time. I got flown down from Boston to testify in federal district court against DuPont in a shareholder called Roosevelt versus DuPont. And you wouldn't believe who it was before. It was before Judge, and this is true, Ruth, Bader, Ginsburg. That was pretty cool. We lost the case, actually. Their lawyers were much better than our pro bono lawyers, but we won because they did what we said they should do. Okay, but in 1991, something happened. Mount Pinatubo went boom in the Philippines. This led to a massive amount of aerosols in the stratosphere. So this is a chart showing something that we call stratospheric aerosol optical depth. It's basically how much sulfate is in the stratosphere. And as I will talk to at the end of this talk, this cools climate and is being used as an analog for geoengineering a climate. Here's how the solar irradiance varies as a function of time. I'll relate this all to ozone coming up. Here's what halogens did over time. This is, again, this EESC. I just want you to realize how monstrous this perturbation to stratospheric aerosol loading was from this volcano and how quiet it's been ever since the eruption in Pinatubo. We have had eruptions that people write a lot about, but they're tiny in terms of sulfate compared to Pinatubo. Okay, so another long story, pretty short. When the eruption went off, what this paper by Simone Becky and John Powell shows is that NO2 went down a lot. That's sort of the immune system of the stratosphere, and CLO went up a lot. I'm not going to read the numbers. These are positive, these are negative. And these two things change, these two important molecules change because of the introduction of sulfate aerosols. Chemistry occurs different on aerosols than in the gas phase. Now, it took us a while to really put things together and figure out the chemistry. But we finally did. I led this paper in 2005. We initially couldn't model the great depth of the ozone depletion in Northern Hemisphere mid-latitudes. This is the anomaly, because we had to get bromine right. And bromine has been kind of the underdog or underappreciated halogen in this whole story. It's been very hard to regulate because bromine's used in two things. It's used as fire extinguishers in regions. A small amount of halons can extinguish a large amount of fire in a very safe way for troops. And so, you know, hard to go away. But what we did there is we said, you know, you're over testing your systems. Why are you testing every month? Do you really have to flush all those halons out? Can't you actually use modern engineering principles and try to figure out how to test without flushing it all out? Bromine was also used as a fumigant, methyl bromide in California. You could read extensively about that, and is still used in some, it's still used in some very, very limited exceptions. The other thing that we did in this paper is we represented natural sources of bromine that are also important. Okay, so again, we had about a 7 or 8 Dobson unit depletion, and that's a 7 or 8 Dobson unit depletion on a background of around 300. So it's a couple percent depletion. And so the depletion of ozone was caused by chlorine and bromine, but it happened because of the volcanic aerosol. The volcanic aerosol turned chlorine away from the reservoirs and into the reactive gases. And how many people in the room are in a class using the 20 questions and answers? All right, so is this like solid? All right, good. Did you like the 20 questions and answers? All right, good. All right, we worked hard on the 20 questions and answers. So in the 90s, the CFCs were replaced by HCFCs. The HCFCs are like CFCs, but they contain a hydrogen, and the hydrogen causes the gases to not be nearly as long-lived or pervasive in our atmosphere as CFCs. Because those who read the 20 questions know the hydroxyl radical extracts the H, abstracts the H in the troposphere. So this was a good thing. We replaced CFCs with HCFCs, and here is some of the new. So here's the time series of the atmospheric abundance of CFC11 and CFC12, which peaked here around the year 2000. And then here are some of the HCFCs, which are peaking 20 years later. That's as much of a detail as I want to go in. Well, actually, one more thing. I'm going to talk about carbon tet at the end. And carbon tetrachloride has been the bane of our existence. We keep thinking it's going to come down, and it keeps not coming down. And I'll talk about that at the end. But what I want to point out is that in about 1998, this thing we call EESC peaked Here are the contributions to ESC from all the different components. The way you read this chart is, the thickness of any color is what the gas or group of gases are doing, but the total EESC is here. Peaked in 98, started coming down, peaked in 98. In 98, the atmospheric release of these gases had really started to fall. Okay, so now I'm going to steer away from the 20 questions and answers for my figures. I had a few that weren't, and talk about an interesting story, a whodunit. So what I'm showing here is different than the atmospheric release. This is the industrial production of CFCs, which were banned by the Montreal Protocol. So this thing is dropping close to zero, but this is now 20 years old. It comes from a chapter in a textbook I helped write, so I get to use this for free. You have to pay a lot to get it. This is the global production of CFCs. Okay, now here are the amount of CFC again emitted into the atmosphere, gigagrams per year in the hundreds. And this was the projection of what it would do, and this is what it did. Oops, they're banned by the Montreal Protocol. Excuse me, what the heck? What's going on here? Okay, so this got a huge amount of attention, including the New York Times, high stakes environmental whodunit, many clues point to China. It was sort of known back then that somewhere in Asia, these CFCs were coming out. This was ground-based observations. And, it is what it is. This paper came out in 2018. Here's a time series showing a deviation way before 2018. The authors of this paper have taken some criticism for not sounding the alarm sooner. Just like I said, Farman saw it sooner. But if you project it here and you're here, is that really a difference? Is it really a difference? Now, oh, crap. And now, okay, where's it coming from? And it takes time to put your story together, time to have an airtight story. And so it is what it is. They got their paper done at this time. We now know that there was cheating on the Montreal Protocol that happened in China. A student who worked with me, Sarah Benish, analyzed aircraft observations obtained over China. We really know, and the Chinese government was embarrassed about this and shut it down. So much so that we see in 2019 and 2020 some really, 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 really good news here. A big drop in the production of CFC this is CFC 11. So we think we're in good shape in getting rid of the rogue emissions. Okay, and I'm going way too fast, but I have some backup material. Okay, so we should be good for the recovery of the ozone layer. We've banned CFCs. We got the rogue emissions under control. EESCs going down. This line shows the change of ozone, 60 south to 60 north, that we ascribe is due to EESC using a mathematical model. We should be good, right? Furthermore, as we have in the 20 questions and answers, this is a comparison of ozone observed, 60 south to 60 north over time. And here is the future climate projections. Now, we do predict a faster recovery of ozone, and the Montreal Protocol, this is very important now, the Montreal Protocol asks us to relate everything to 1980. It's kind of built into the Montreal Protocol. So we always have to do this, even though we had ozone depletion prior to 1980. But it's good to have a common benchmark. And we had a lot of good data in 1980. So here's the 1980 level. We should scream through this under a high climate forcing scenario, SSP 37.0. That's 7 watt per meter squared radiative forcing by end of century. That would be disastrous for our climate, but good for the ozone layer. Hopefully that won't happen. And this is predicted by the models because some circulation in the stratosphere, we call the Brewer-Dobson circulation, is predicted to accelerate. And that acceleration will take ozone from the ozone production region in the upper stratosphere and bring it down to the lower stratosphere where it just accumulates. Whether the model's really right or not, we don't know. And then, you know, with a low climate forcing scenario, we have basically a permanent turnover of ozone, and I can't tell you why. Does anybody know what gas is responsible for this? It's one of the greenhouse gases. If you've read the 20 questions and answers super carefully, you may know. Oh, it's going twice. Nobody? Okay, it begins with an N. Greenhouse gas. N2O. Nitrous oxide. Nitrous oxide is the ozone depleting substance of this century. And in all the climate scenarios, nitrous oxide keeps rising. And it keeps rising because it's a product of the world's agricultural production of food. So this is why we have a permanent depletion of ozone in this scenario. Here we've gotten CO2 and methane under control, but we haven't gotten nitrous oxide under control. And long story short, for the Antarctic ozone region, we're much less sensitive to other gases besides chlorine. Whereas where people live, we're more sensitive to the other gases. So this is some of the complexity, but nonetheless, we should be good, right? Wrong. So here's the problem. The problem is we're not seeing ozone in the Northern Hemisphere move. At Northern Hemisphere mid-latitudes, the change in ozone over this 24 or 25-year period is 0. It's not moving. We're getting some increase in ozone due to the decrease in chlorine in the Southern Hemisphere, but not in the Northern Hemisphere. Here's the same thing in a picture. The picture is the data. The red is the data. The green is what we expect should be recovering if all things were being equal. And here is here's the depletion over this time period. Here's the recovery. I would have put the pivot date a little bit later, maybe 98, but where exactly you put the pivot date doesn't matter for this sort of thing. Ozone isn't going up in the Northern Hemisphere. And I showed you that in my very first slide. You can see it. You don't have to do any stats on it. You see it's, if anything, it's going down a little bit. So the rest of this talk will be explaining some of that, and I'll leave a lot of time for questions, and I do have backup. Okay, so first off, we have several problems. One problem is that EESC, equivalent effective stratospheric chlorine, is not doing what we thought it would do. So this comes from a paper that Megan is leading that is back for the second review. We have fingers crossed it will review well. What we're showing here, and I'm sorry I didn't put the word mixing ratio here, my bad. I just extracted one panel from a 4-panel or 6-panel figure. This is the mixing ratio in parts per trillion of this quantity EESC. Now, what we're showing here is the projection that occurred in 2006, back when all the world scientists got together and came up with an estimate. And 4 years later, in red, then blue, gold, and purple. What we're showing here with these sticks going up is the year in which we expect EESC will return to the 1980 level, because that's what the Montreal Protocol wants to know. So over this 16-year time period, we've had a 13-year delay in when we expect chlorine and bromine to return to the 1980 level. Houston, we have a problem here. And so I think this paper that Megan is leading is going to be an incredibly important paper, because it shows why we estimate we had a problem. So of this delay, we have about 4 years due to how we estimate banks. What are banks? Banks are not where you put your money, not in this term. It's where you put your CFCs as you're using them, like refrigeration equipment, which is supposed to be vampired, get the CFCs out of it, and they're supposed to be incinerated. But when do you call for your car air conditioner? When do you go in to have it fixed? When it stops working. Why does it tend to stop working? Because the coolant leaked. Once it leaks, it's in the atmosphere. Also, people abandon refrigerators even though they're not supposed to. And there's been like exposés on the news of some companies they're supposed to extract, but they just take the refrigerators to landfills and let them rot. This is in the US Southeast. You can go Google it and find this stuff. Another issue is recovery, and this is a hard one, is recovery of CFCs that were used as insulation and foams when buildings, from the 70s are torn down. The wrecking ball comes and everything in the foam just gets released to the atmosphere. But nonetheless, there could be an aggressive way to go after this. We also have something that we have no control over. These are ranked in terms of the magnitude. We have no control over what scientists think the lifetime of the gas is. Our knowledge gets better over time, we hope. And so as our knowledge gets better, we think these gases are longer lived. If they're longer lived, they persist for longer. I mean, it is what it is. We do have control over the emission of carbon tet used as a feedstock. The Montreal Protocol bans the production of all the ozone depletion substances for something we call emissive uses. Those are uses where you expect eventually it will be released to the atmosphere, including refrigeration, even though there are ways to keep it from release. But as I said, usually this equipment eventually leaks. We do allow gases like carbon tet to be used as feedstock for making other gases. And the dang on problem is we tend to be leaking it to the atmosphere. So maybe we should tighten the controls on feedstock emissions of carbon tet. And then basically, I think that cheating on the Montreal Protocol is probably a little bit more than this, but we think that cheating on the Montreal Protocol, which got all the headlines and all the news, is a fairly small part of this. The big part is feedstocks and people previously underestimating how much we were leaking out of CFCs made 20, 30, 40 years ago. Banks and feedstock are the big players, and cheating is a small player. And I think this paper will be very important. Any questions? Okay, moving on then. Yes. Very good question. We have the world's expert on this in the room. Are there biases in the release?
I would say large and certain. So we have a general sense of how large these reservoirs and things are, but there's a large part. And historically, I think we have been biased in our
That because we want to protect our emotions as people.
just more reporting on the action.
Yeah, I'll take that on. That's a really great question. And I think that the answer to your question is, are there biases, emotions? I think really honestly, it's a hard no with a caveat. I think that the people who do this are extraordinarily good-natured and really are trying to do it right. Now, some of them have industry ties, but some of the champions in this whole thing have been people with industry ties. Like a guy, Mac McFarland, who's no longer with us. He worked for DuPont, been champions in getting DuPont to say, they're right. We got to stop this. Okay, so I think that people have been very good-natured and good-willed. I think that Megan has picked a very hard problem to work on with a lot of uncertainty. So she's courageous. I think the human emotion does come in for not wanting to admit you're wrong. So, people publish stuff and want to defend it. And that is something that those who want to go into science are going to deal with, both with yourself and your colleagues. And, it takes a pretty emotionally and intellectually mature person to admit you're right, I'm wrong. You don't hear that too often. So I think that's where the human emotion comes in. But I don't think it's ill-willed. Great question. Great question. Okay, let me talk about this slide. What I'm showing over here is, sorry. Okay, what I'm showing over here are a time series of 4 gases. These gases have chlorine in them. They make it to the stratosphere, and they're not regulated by the Montreal Protocol. And they're not regulated by the Montreal Protocol because, they're very short-lived. They say they won't make it to the stratosphere, but they do, they do, they do, they do. These are observations obtained in the tropical upper troposphere the entry point to the stratosphere, showing, let's focus on this. Over time, the total chlorine content of these gases has been rising. This is the work of Ryan Hassani and Martin Chipperfield in University of Leeds, who are authors of this figure that appear in the assessment. Okay, this is a big mess over here. What we're showing in green are data for total column ozone, and it's my group's attempt to model this. Now, this is 60 north to 60 south. And what we're doing in this model is we're not allowing for the influence of very short-lived chlorine gases. We tend to have an underestimate of ozone here. These numbers are a little low. We have a mean bias. I think that says mean bias recent. That's over the last 10 years of 0.65 Dobson units. So we're not doing a great job. If we put very short-lived chlorine in, we do a much better job. We reduce our bias by a factor of 2. We don't remove the bias, we reduce it by a factor of 2. You can see how the graph changes. So the black is our model is going down. And what I'm pointing here is the year in which ozone will be 50% recovered from the depth of the depletion due to stratospheric chlorine. So 2030, I can start thinking about 2030, planning for it. If the good Lord is willing, I'll still be here in 2030. Now we're pushing this out to 2038. Now I got to start doing the math. Let's see. 64 plus, I don't know. Okay. This is keeping very short-lived chlorine fixed. What if it's rising at the observed rate of rise? Now we're out to 2043 before we have the 50% benchmark. If I'm here in 2043, I'm not going to be walking like I'm walking today. I hate to say it. It is what it is. Father Time's undefeated. Okay, so not so fast for the ozone recovery. And this is stuff we're working on getting out. Okay, so let me talk about some successes.
This is on top, this is different than the ESC. You're showing dates that are earlier than the expected ESC.
Okay, yeah. So this is the effect of EESC on ozone, but this is not returning to 1980. This is returning to halfway to 1980. So this is the halfway point. Yeah, if we never get back to 1980 in this world. Yeah, this is no, great question. I want this to be clear. And, the kind of conversation we have is, if we project out to a time where people can conceive of these times, it's a much more powerful statement than going to the end of the century. So we invented the halfway point as a way to illustrate this. Okay, so let me talk about a few successes, and then I'm going to come back, and I am actually I've slowed myself down. I put the brakes on, so we're good time-wise. In fact, I'm probably a little bit behind. All right, so we replace CFCs with HCFCs. Okay, but HCFCs cause some ozone depletion, a little bit. So then we replace them with HFCs. HFCs have no chlorine in them, no ozone depletion. Yay, save the ozone layer, right? Nope. HFCs cause lots and lots and lots of global warming. So we, the ozone community, took HFCs away from them, the Kyoto Protocol, the climate world, the Paris Climate Agreement. Like, y'all ain't doing anything. You say you're going to do something. We're taking them. We have the connections. We have the industry people we work with. We know how to do this. So in January of 2019, Tina is here, Constantina, the Madam Secretariat. She's very formal position. She got here by having a PhD in environmental management economics from Imperial College. She's wonderful. What happened is basically we're going to really reduce the emission of HFCs with high GWPs, global warming potentials, over time by replacing HFCs with gases that have the similar, almost the same cooling properties. So if you have a heat pump in your home, it likely has an HFC in it. We're replacing them with gases that have a fragile chemical bond in the middle that causes them to decompose when released to the atmosphere. They're called olefins. It's going to save us a whole lot of warming in the future. Here's the warming, business as usual. Here's with the replacement of the olefin gases. This is a giant success. We're going to get rid of half a degree warming. Here's another giant success. This is the number of skin cancer cases. This is just for the US, and I'm trying to put together a paper. This is my next huge collaborative project to do this for the whole world and trying to get ready for the next assessment. Once our BAMS paper is submitted, I'm gonna start action on that. Okay, so we've saved a huge amount of skin cancer. All right, but here's the last part of my talk. We have trouble ahead. The trouble ahead started sort of in 2006 when Paul Crutzen published this paper, talking about putting sulfur in the stratosphere to mitigate climate change. Who is Paul Crutzen, you might add? Well, remember I showed you a picture of Mario and Sherry with the King of Sweden. Paul was up there as well. There were 3 laureates in 1995 for work on the ozone layer. When you get this award and you publish a paper in a fairly obscure journal, your paper gets a lot of attention. So following the 2006 publication of this paper, and Paul is great, Mario is great, Sherry is great. Sadly, none of them are with us anymore. I've known all of them. I've laughed with all of them. So they're all just great. We had a National Academy of Sciences report called Climate Interventions, turned into 2 volumes. This is the 2nd volume, Reflecting Sunlight to Cool Earth. Stratospheric aerosols, blah, blah, reflect sunlight into space or marine cloud brightening. Both are very controversial. You could Google it. They're extraordinarily controversial. We had another report come out in 2021, Recommendations for Solar Geoengineering Research and Research Governance. And we had a chapter in the Ozone Assessment Report that Megan and I work on, devoted to all of this. And next 2 weeks from now, there's a meeting here in DC, NSF, exploring the ethics and societal interactions of climate intervention. If you go to the website, it says applications are now closed to join this meeting, but I got in. Here's the email. Fortunately, they said acceptance in the title. It says, Dear Ross, thank you for your interest. We received an overwhelming number of applications. Okay, that's going to be bad news. Oh, wait, no, they said acceptance. Okay, so I'm invited to this and this to talk about this issue. All right, so here's the bottom line. You may have learned that when a major volcanic eruption like Mount Pinatubo occurs, it leads to about a half a degree warming for months or even years. My God, the IPCC wrote this in 2007. This is in the scientific echo chamber. And it's a bit of an exaggeration. It's a long story, but it was based on a flawed measurement of observations that were not what we're actually regulating, which is surface temperature. One of the papers that shows that it's a bit flawed is this paper that Laura led. Ooh, I don't have her say. This is McBride et al., 2021. I want you to take away 2 numbers from this. Here is our estimate of how much cooling we had from volcanoes. Pinatubo cooled at most 0.3 degrees. It didn't last for years. It lasted, the deep cooling was very short. And also we're warming climate at about 0.17 degrees per decade we get out of our model. I don't have time to explain the model. Finally, IPCC has come around, and here's their cooling after Pinatubo, whatever figure number this is, figure 7.8 of AR6. So what we do, here's the 0.3. So what we do is we put these together. Here's the stratospheric aerosol optical depth after Pinatubo. Here's the ozone depletion that happened. This is about a 2% drop in ozone. Here's the cooling that happened. So if we're worried about offsetting 0.17 degree per decade warming, that's how much we're warming, we're going to reduce column ozone by about 4 Dobson units per year. If we do that, we're going to have a 4 Dobson unit per decade, is all per decade. So we'd be causing about a 2% per decade rise in the bad cancer, a 4% per decade rise in the less bad cancer. We also would continue our dependence on fossil fuels, all the air pollution. We wouldn't address something very few people talk about, ocean acidification, which is going to devastate the world's ocean ecosystem. And there have been papers that say if we do this, we're going to threaten the viability of the Asian monsoon. Because after Pinatubo went off, the amount of sunlight reaching the surface went down some, cooled. But what really changed is the ratio of direct sunlight. When you look at the sun, you have to cover your eyes, to diffuse sunlight. That changed dramatically. And the Asian monsoon relies on that direct sunlight to evaporate. Trees actually like the diffuse sunlight better. Trees would like this, but they don't get to vote. Okay. I love trees. Okay, national trends in cancer. I pulled this from a US agency for women. Melanoma is sadly the largest rising cancer. For men, it's rising as well. Obviously, some of this is behavioral. A lot of it's behavioral. But if we reduce ozone, we expose more people to UV light. So on that happy note, and let's see how I am time-wise. Okay, I think I'm good time-wise. I am happy to take questions. Yes.
Questions for Ozone, but given the kind of stuff you added at the end, would you add any questions to that list now?
Wow, that's a really great question. For the people online, Jen, what's your name? Alex asked, would we add material to the 20 questions and answers? The 20 questions and answers is a bit of a political beast. It has to represent consensus of the community. It's not my view, it's not the co-author's view, it's something that everyone can embrace. So it has to flow from the chapters, and it has to be something that we hope we never have to go back on. So it's, people have asked me why I do it. Also, I don't get credit for it in my Web of Science citations. It's not in, it's the long story because it's not peer reviewed. Well, it is reviewed, but it's not peer, the review's under our control. We decide who reviews it, but we get like dozens of reviews from the players in the ozone assessment. So for something to reach the 20 questions and answers, it has to be very consensus driven. I tried to get this figure in there. I could not. And I could not because I couldn't get the lead authors of the geoengineering chapter to agree to having this figure in. Here's what they said about it. I'd give long answers to questions. They said, well, this figure is misleading. It's misleading because chlorine was higher when Pinatubo went off. It was. Than it will be in the future when we might geoengineer climate. That was a purposeful Freudian slip. When we might. And we're like, yeah, but it's only like 10 or 20% lower, and plus VSO chlorine, it's not going down as fast as you think. Okay, then, well, it might not be stratospheric sulfate aerosol. So using Pinatubo as the analog could be very misleading. What if we put a different aerosol? We're like, well, let's put this figure in and make it very clear we shouldn't put sulfate in. But sulfate is being talked about because A, we know how to do it, and B, we could actually financially afford it. So people have run all the numbers. So it becomes extraordinarily contentious getting new elements in. On the other hand, we will soon be convening a new author team. And every time we have a new author team, you know, a figure or two will change. But the 20 questions is a slow moving vessel. But I am working on another paper, which is, so I'm like, I don't know what, I have two sides. I have my consensus building, voice of the community side, and then my other side. I'm working on another paper for submission to BAMS, the Bulletin of American Meteorological Society, that's talking about how the stratosphere is an unsolved problem. And this figure will be in that paper. So I'm trying to have my cake and eat it too. More questions? Yes, in the back.
Recently, there was that huge chemical burn outside of Atlanta, Georgia. And apparently there was chlorine going up into the atmosphere. What sort of impact does something specifically like that have on what you're?
Really great question. The question was the chemical burn outside of Atlanta and chlorine being released. I don't know much details about that, about what actually was released. but most of the chlorine that's released is very dangerous in the immediate time and place of the leak because it's reactive chlorine. We are worried about a special class of molecules that are unreactive, and I don't think the class of molecules that we know could reach the stratosphere were released, but I'm not really sure about that. I can only infer that because the authorities had a huge evacuation locally, and that meant that these were biologically reactive. So probably they won't make it to the stratosphere. The other thing is that for air to enter the stratosphere, the stratosphere is called the stratosphere because it's stratified from the troposphere. It's stratified from the troposphere because only a few special places does air punch through the tropopoles and reach the stratosphere. One place we know it happens all the time is the tropics. If anybody's been to the tropics, in certain countries in the tropics, like Singapore, or Costa Rica, it can rain every day like clockwork at 2 p.m. And by 3:30 p.m., you have no idea that it just rained. I mean, it's a torrential downpour, and then the sun just evaporates it. So those torrential downpours are associated with uplift, air gets to the stratosphere. Other place air gets to the stratosphere is over India during summer and over North America during summer, the Asian monsoon, North American monsoon. So if pollution from, say, Chicago gets caught up in the summer monsoon, it could actually make it in the stratosphere. And we had a whole mission studying that in Salina, Kansas a few years ago. So you need special cases to get the air into the stratosphere. And, well, sadly, what's going on in the Southeast, the hurricanes don't generally get anywhere near high enough to threaten the stratosphere. It's more tornado kind of weather, if you will. Okay, more questions. Peace sign.
So obviously, you have HFCs and CFCs, they're supposed to be better replacements for. Is there any other material that scientists are kind of worried about on the horizon that might be another potential dangerous gas or material?
Great question. I repeat also to give me time to think about it. What's your name? Evan asked, and sorry for not getting your name in the back. Okay, thank. Evan asked whether we're worried about other materials besides HFCs HCFCs replaced with HFCs. I'm going to answer it in two ways. First off, hindsight's 2020. I think that we dodged a bullet with HFCs. Some of my colleagues might not like me saying this, but I think that we kind of moved over aggressively away from HCFCs and into HFCs because HFCs have much higher global warming potentials than HCFCs. And so we kind of overreacted, if you will, or jumped the gun, but industry was involved with this and there were good industrial reasons for HFCs. We got lucky that we could figure out a way to replace HFCs with these olefins. Now, the olefins do decompose in the troposphere, and people are concerned when they decompose in the troposphere, they could cause problems for wetlands. So there are people looking at the decomposition products. I would say the jury is still out on that, but more people think that the decomposition products of we call them HFOs. The O doesn't stand for oxygen, it stands for olefin, which is a double carbon bond. Most people think that the decomposition products of these olefins are benign, but I would say the jury's still out. The big gas on the horizon we had already talked about, and that's nitrous oxide. So, the Paris Climate Agreement. Are we going to limit CO2? Well, we'd love to limit the growth of CO2. I actually have it here all the way at the end, right? We would love to keep CO2 from rising, but we ain't doing it. Methane will probably have some success at because it's a low-hanging fruit, like landfills and stopping leaks. Nitrous oxide is just lost. It's just lost. So there are folks who are talking about trying to bring nitrous oxide, N2O, under the umbrella of the Montreal Protocol. That is a huge hill to climb. The hope for climbing the hill is that if we don't do it, nobody else is going to do it. It's just lost in the conversation. And here we have to come up with a way to grow enough food to feed the world that's less nitrogen fertilizer intensive, perhaps figure out how to grow rice without releasing so much nitrous oxide. So it's a very specialized application that needs a lot of TLC, tender loving care, that I think, you know, that the tall poles are behind us with the Montreal Protocol, although I think they will have to do something about the very short-lived chlorine gases too. So I would put very short-lived chlorine gases and nitrous oxide as what we're most worried about in the near future.
Thank you so much for a wonderful talk. Let's give our speaker.
Thank you, thank you.
Reminder that there's a postdoc lunch following this in region 391. 391 with Ross, and there will be no eco talk next week. It's a holiday, but the following week there will be one on with Dr. Omar Tesla, who's traveling all the way here in Palestine, and we'll be talking about tree crops and regenerative tree crops in Palestine. Thank you all for coming.